Okay, so we're going to round off chapter 12 with section 12.4. It's called, I believe it's just called the normal curve. So the normal curve, if you're going to go into any statistics or large population study, you see it time and time and time again. And so what this slide is showing us is that sometimes if you have kind of a small sample size, and 100 seems like a big number, but it's not really that big in the grand scheme of things, then if we're going to have some sort of average that will show up, we don't have kind of a weird situation where maybe you could only have men of height of um, 7 feet and only men of height of 2 feet. Uh, if we have kind of a normal, hence the title, something that we can sample in a large size, it always seems to kind of fall into the shape once we get enough points. And so that's kind of something, I believe it's called the law of large numbers, that yeah, maybe if you only have 100 data points, you can see kind of this bell curve that's happening part A. And maybe if you double that amount, you get something that gets a little bit closer to the bell curve, but maybe is a little bit skewed towards the center or something. And then as you continue to increase and increase and increase, and when you start to get into samples of like 10,000 people, you start to get this shape every time, this normal curve. So that's why it's a really popular distribution, as it shows up again and again and again and again as long as we have enough data points. So to start kind of talking about the standard deviations and why we even were talking about, or not, sorry, the normal curve, but why we were even talking about standard deviations last class period and last lecture. As I mentioned, kind of the surface intuition is that big standard deviations mean the data is spread out pretty wide, and small standard deviation means it's kind of clumped around a single data point. Well, there is this rule of a 68, 95, 99.7 rule that tells you that if you are, let's say that you want to find a data point between one standard deviation above and one standard deviation below your mean, your average. So on this figure, we have the mean is 0, right in the middle of the graph. And so if I were to pick a point randomly, there is a 68% chance that it will fall between in that red region. So to give that a little bit of context, I think we'll see an example in the next slide, but let's say we were going back to the height of men, and let's say that the average was, I don't know, 60 inches. And so if the average was 60 inches and I had a standard deviation of 5 inches, that means that if I were to just randomly ask someone that took that survey or that was observed in that trial, there's a 68% chance that they will be either, I don't know, between 65 and 55. I believe I said the standard deviation was 5. So that's the idea, that randomly picking someone, there's a 68% chance that they will be between one standard deviation of the mean. And there is a 95% chance that someone randomly picked will be 2 standard deviations away from the mean. And there's a 99.7% chance that there will be 3 standard deviations away. And we can go on and on and on. And 99.7% is pretty good, right? If we have a very large amount of people, we can say, hence the term confidence interval, that if we were to randomly pick someone, there's a very, very, very good chance that that person will be within 3 standard deviations of whatever your mean is. Of course, we can't ever get 100%, right? Even if we were talking about 10 standard deviations away, which would be 99.999% chance of you just kind of picking someone at random would fall between the 10 standard deviations above and 10 standard deviations below the mean. There's always going to be the chance of just picking an outlier, picking someone that is a giant, or picking someone that is super small, or maybe, again, maybe the data was put in wrong. Maybe someone just was typing in the data and they put in 500 inches tall, which is possible, but that could potentially happen when you're gathering a data set. So that's always something that is a possibility, that someone just entered in some sort of data wrong. So All that's aside, that's where we're talking about the standard deviation. And so that's where we start to get some intuition about what that actually meant. Talked about last time, big standard deviation means that we have a wide spread of data, but now we know that specifically it's going to tell me like where 68% of my data points lie between. It's going to be one above the mean, one standard deviation below the mean. And so with that in mind, great, yeah, we have an example right here. We are told that male adults in North America are approximately normally distributed. And it's going to have to tell you that because there are other distributions, we just don't tend to talk about them a lot, certainly not in this course. So if the question is properly written, it should tell you that it's definitely calling into kind of this normal distribution, this normal curve. So we're given that in this question. We're told that the mean, you know how to find mean, we found that before, is 70 inches, and then the standard deviation is 4 inches. So we want to figure out the height that is 2 standard deviations above the mean. Well, that's actually not too terrible. You just take the 70, multiply your standard deviation times 2, and you get 8. So 8 plus 70 is 78. If we want to find something that is 3 standard deviations below the mean, very similar process. I take 70, I take 4 times 3, I subtract that from 70, and I get 58. So that is kind of the easier type of questions we can ask involving normal curves and standard deviation. But to get a little bit more involved on this next slide, let's ask some more interesting questions. I guess interesting is all relative. But let's say the same type of thing. We have male adults, we have the mean 70 inches, the standard deviation is 4 inches, so just what was on the last side. Find the height that is between 66 inches and 74 inches. Wait, sorry. Yeah, sorry. I kind of spliced 2 questions together. So the question now is I want to find the percentage of men in North America that will fall in these regions. So the first region is 66 inches and 74 inches. And so we're going to have to kind of go back to this rule. Is 68%, 95%, and 99.7%, because these are the most common things we talk about with normal distributions. Yes, there are other percentages, like you can talk about being 2.5 standard deviations away from the mean, but outside of having a fancy table, this is what we're going to see most often. Is it 1 standard deviation? Is it 2 standard deviations? Is it 3? So really this first question is asking us is which region are we falling in? Are we falling in the red region? Are we falling in the red region and the purple region? And so in order to determine that, we have to figure out what standard deviation we're talking about right here. So I know my mean is 70 inches. I know my standard deviation is 4 inches. So I want to find the percentage of people that fall between 66 inches and 74 inches. And so this confidence interval, this interval that we were talking about that breaks down these regions into the 68% and then 95% intervals, we find what region we're in by taking our mean, adding and subtracting the standard deviations, and then that A is going to tell me how many standard deviations away I am from the mean. So for part A, I know my mean is 70. I'm trying to find the amount of people that are between 74 and 66. And so I just set up my equation. Plug in mean is 70, plug in standard deviation is 4, plug in my confidence interval is 60 or 74, and I solve for A. And so my A is 1. And I should do the same thing for 66 inches. But if I do the same thing for 66 inches, I will also find that my A is 1. And so what that tells me is that this region that I'm trying to describe, the percentage of males that I'm trying to describe, are going to be 1 standard deviation above and 1 standard deviation below the mean. So I think I come up with a picture. Maybe the order is a little bit off, that's fine. So I'm looking back at this picture of my confidence intervals that I looked at from 2 slides before. And I see 1 standard deviation away from the mean is that red region. And that nicely falls into my 68, 95, 99.7% rule. So it's just 68%. 68% of my data points fall in that red region because it's 1 standard deviation above and 1 standard deviation below my mean. And so anytime I do these problems, I kind of recommend having people draw the picture of what region we're describing. Sometimes it's nice and we just say, oh, it's the red region, or oh, it's the blue and red region right in the middle. But that's not always the case. And so do the math to figure out what you're describing, how many standard deviations above the mean you are, how many standard deviations below the mean you are. And then from that picture, you can start to kind of reason or kind of solve a puzzle to figure out actually what percentage of people fall into that region. So we're going to see that more in part B and certainly a lot in part C. So now part B tells me I want to find the percentage of men that fall between 70 inches and 74 inches. And so 70 inches is my mean. So I know that part of my data is going to be right on the mean. So I'm 0 standard deviations below my mean on the bottom end. And then I also know from part A that 74 is 1 standard deviation above the mean. So looking at my thing, I put in purple what region I'm describing. I'm describing the area for my mean to 1 standard deviation above my mean. So I take that red region and I divide it by 2. Like I'm still looking at the red region, but I'm only looking at the top half, not the bottom half. And so if I take 68 divided by 2, I find that 34% of men are going to be between 70 inches and 74 inches. So it's not always cut and dry to look just at a purple region, just at the red region. So that's why it's always good to kind of have that normal curve as a reference. Honestly, that picture that I have pulled up is really nice because it makes it so you can kind of clearly circle what region you want to. Sometimes if I don't have that picture, I personally just draw it and label it almost exactly like this. But I don't know, in your notes or whatever, I would maybe, if you're taking electronic notes, maybe copy and paste it over, or maybe if you're taking printed notes, you can cut it out and paste it in there. Whatever you need to do to make it so that you can kind of reference this puzzle and put all the pieces together. Because for this last question's pretty involved. I want to find the number of males that are above 78 inches. Now notice I don't have a region anymore, right? I don't have between 70 and 74, between 66 and 74. I just have kind of a blanket statement above 78 inches. My starting point is still going to be the same. I want to figure out how many standard deviations away this description of 78 inches is. So I'm going to do that again. I'm going to kind of do what I did in part A. 78 is equal to 70 plus 8 times 4. 78 minus 70 is 8. Divide both sides by 4, I get 2. So I know that 78 is 2 standard deviations away from my mean. Now, if I look at the region that is 2 standard deviations away from my mean, I don't know. Oh yeah, okay. So I know this blue box is now what I'm describing, right? It's everything above 2 standard deviations away from my mean. Now I'm looking at kind of this breakdown on my chart, and in order to describe the blue region, I need to maybe describe what's missing. Because if I can kind of describe everything that's below 78 inches, I can say, well, I should have overall 100% of my data, so I can kind of subtract what I have from the overall thing. And that's kind of the approach that I'm going to use. And that being said, the approach I'm going to use might not be the most straightforward to use. So you might find a different route to describe that region, to kind of puzzle out that light blue region. And so if that works for you and that makes sense to your brain, you don't have to follow the route I'm about to do. But here is the route that I did. I said, okay, I'm going to describe the green region. Well, the green region Anson changed. So like we can see kind of towards the very bottom of the curve between 2 and 3, there's a light tinge green there. I'm going to try and describe that, but also that and then kind of everything to the right of it. And I notice that everything that I see right here, the blue and the red that isn't green, that total region is 95%, right? From -2 to 2 standard deviations away from the mean, I have a total of 95% of my data. So that means all I have left for the stuff that's outside of that region is 100 minus 95. So that tells me that 5% of my data falls outside of the red, outside of the blue. Now, once I found that amount, I found kind of the right wing of my standard deviation or my normal curve, and I've also found the left wing, but I only want the right wing. So if I only want to describe the amount of data above 78 inches, I have to take that 5% that I found and then divide it by 2. So that tells me that the region above 2 standard deviations away, the amount of males above 78 inches is 2.5%. That is a tricky example. The good news is that I need to double check this because I've been saying it a lot, but I believe there isn't any statistics questions on the exam. And so this might be kind of the hardest question you might see on my math lab. But as always, I kind of throw away 2 points of my math lab. So if you're tracking with everything else in this normal section and you can't quite get one of those difficult questions, that's fine. Maybe just go ahead and skip that one, or give it a shot for a while, and then if you get frustrated, go ahead and skip it. Okay, now z-scores. So as I mentioned, kind of this diagram, maybe I shouldn't go so far back. Yeah, here we go. This diagram is kind of the nice cases. We talk about 1 standard deviation away, 2 standard deviations away, 3 standard deviations away, but that's not always going to be the case. In our example, it just so happened that magically everything was either 1 or 2, or well, I guess that's it, 1 or 2 standard deviations away. But what if I wanted to talk about males that were between, I don't know, 68 and 72 inches? Well, that's not 1 standard deviation away. That is half of a standard deviations away. So to kind of provide some regularity to these problems, we can find this idea of a z-score. And to find what a z-score is we take our data item that we're trying to find, like I said, with a 72 inches tall or something like that. I subtract my mean, I divide by my standard deviation, and that will tell me how many standard deviations away I am. So that's pretty much what we were doing here on the top. I just didn't have the thing formally written. And so the reason why we do this is because, I mean, we don't necessarily have nice things to get. We could have 0.5 standard deviations away. We could have 0.91 standard deviations away. That can happen. But also, if we find this z-score, there is a table in almost every statistics book. It's almost at the very back of the book because you have to reference it again and again and again and again. That has a normal table. And with that normal table, you can take any z-score that you could possibly find. You can look at the table, and it's going to give you a result of how many data points are below that z-score that you find. So that's not something we're going to do in this course, but just in case you want to go into statistics later on, z-score is a very popular topic because it makes it so that you can find this percentage or this confidence interval for a normal curve with any data point. Doesn't have to kind of fall into the nice 1 standard deviation away or 2 standard deviations away. And so kind of building on that idea of a z-score, what the z-score returns is this nth percentile. And the nth percentile is the number of items that are less than, or the percentage of items that are less than a particular value. So a percentile for this question, I found that for 78 inches, people above that is 2.5%. If I wanted to talk about the percentile of 78 inches, that's always less than. And so in this case, I don't know, it would be 97.5% of the percentile of 78 inches is 97.5%. Wait, hopefully I didn't give it away. I did give it away. Okay, that's fine. I'm glad that I was thinking that was super important. So yeah, that's what we're talking about with percentiles, is we are figuring out just very specifically, standardly, only caring about what's below it, which kind of makes sense. I feel like when I was growing up, I heard percentile rank a lot when we're talking about kind of taking standardized tests or taking exams, because that's kind of what the grade is supposed to be. Yes, in our course, 95% doesn't mean you have 95% more than other people, but if you took the GRE, or if you took the SAT or the ACT, or I mean, pretty much any standardized test with a large amount of people taking it, they are giving you the percentile rank. That isn't really your percent score. That's just in comparison to all people where you ranked. So another example is if you have a really, really difficult test, sometimes like getting a 10 out of 40, that's a failing score if you just go straight with the points. But if it's really difficult, that you could have a high percentile rank because that's just in comparison to other people. That isn't necessarily like an overall grade. Now, margin of error, this is kind of interesting, especially when we're talking about kind of the politics that are happening now in the world, that if you see kind of these polls or who's ahead or who's behind or how many votes are going which way or that way for different states, if you're watching the news or something, they kind of tend to post in big bold the results of, oh, this person's ahead by 42% and 90% of votes have came in from North Dakota. And then at the very bottom, you can kind of see there's a margin of error. And that's because that's always going to happen. It depends on how many data points you gather. If you gather a lot of data points, like in the billions and trillions, your margin of error is going to be pretty small. But if you only gather like 10 data points, and sometimes they don't really gather that many when they're making these suppositions on the news, you're going to have a very large margin of error, which tells you kind of how likely it is that what you're looking at is just plain wrong. Like that's the idea of margin error of a survey of if they say we have someone ahead to win in South Dakota by 20%, and they've only really asked like 100 people, they have a very, very big margin of error to the point that you should probably ignore it until they have more polls to come in. So that's the kind of application thing. To calculate your margin of error, it doesn't really matter what your mean is. It doesn't really matter what your standard deviation is. All you do is you take the amount of people that were asked, n, you do 1 over the square root of n, and then you times by 100%. And so that'll tell you the margin of error of, oh, how likely it is that what we're seeing is within 95% of a chance of falling above or below this whatever margin of error that we're looking at, the mean or the result that we're looking at. So in this case, shows that a table, we don't have the table, it doesn't really matter. Let's say there was some survey of a random sample of 1,000 US adults, and 46% of those questions said that they dread public speaking. It's kind of low, but it's whatever. So I don't know why it's saying verify. That seems kind of poor language. We're going to find the margin of error for this survey. So it's actually not too terrible in the grand scheme of what this section's looked like so far. We're tripping up in my speech right now. And that all we do is we look and say the survey has 1,000 US adults. And so I take the 1,000, I take the square root of 1,000, 1 over the square root of 1,000, I multiply it by 100. And so with this survey, there is a 32% plus and minus margin of error. So if we took a very large survey is kind of what it's getting at, truly almost all the time we could say if that margin of error was really small, that it would be 46%. But what this is telling us is that it's a pretty decent survey size. 1,000 US adults isn't too terrible, especially maybe if you're only looking at kind of the results of a small town. But with that result saying that 46% people really question or dread public speaking, we can say that's probably true within a 3.2% plus or minus. So maybe it's more likely that if we kept asking people, we would see that actually 49% people dread public speaking, or maybe only 43% dread public speaking. And again, that's kind of a 95% chance they'll fall between those two values. So there's a good chance, a very, very good chance that in the grand scheme of things, if we ask a ton of people, that actually 46% plus or minus this 3.2% dread public speaking. So that's this idea of margin of error. It's kind of people conceding, hey, we have this result. This is what we think. This is how many, the percentage of people that are voting for this senator versus the percentage of people voting for this senator. And then, by the way, in really small text at the bottom, we're going to tell you that the margin of error is plus or minus whatever. So if it's super small, you can kind of take it and say, okay, that's clearly going to be the result of the state. Or if it's really, really big, they probably haven't really asked that many people, and you should wait to kind of see that until that margin of error drops down so that they can ask more people. And a keyword that is kind of being glossed over in this example is random sample again. That's something that I think we talked about, if it wasn't the first section, the second section, that if we're talking about these margins of error, we kind of have to assume that there's almost no bias or very, very little bias when taking these surveys, because otherwise then we're not really getting a good result. Like, this margin of error is kind of meaningless if your thing is actually just wrong. Like, if you only surveyed people that were lawyers or people that were debate champions, then you're going to say that 0% of people dread public speaking, and so then the margin of error is going to become meaningless, because that's just clearly not true. There's more people than 0% that dread public speaking. Okay, and so that's it for statistics.